I had a request from a student to go through one of the correlation questions using the formulas that have the standard error for R and the t-test. And so I picked this question, question 16 from the textbook. I typed it out so that we could see it, have the visual here. And it says, as we've noted in previous chapters, even a very small effect can be significant if the sample is large enough. Suppose, for example, that a researcher obtains a correlation of R equals 0.6 for a sample of N equals 10 participants. Is this sample sufficient to conclude that a significant correlation exists in the population? Use a two-tailed test with an alpha of 0.05. And then B increases the sample size to 25 and asks the same question. So if we're going to do this question or complete it using the standard error of R and T, it starts out the same. In terms of the four-step hypothesis testing procedure, step one is the same. We've got our null and we've got an alternative, right? And for the null, and this is a two-tailed test, okay? So the null is rho is equal to 0, and the alternative is that rho is not equal to 0. And both of these are going to involve rho versus R because it's the hypotheses are about populations, not about the sample. Our degrees of freedom is n equal or n minus 2, and in part A, that is 10 participants subtract 2, so we have 8 degrees of freedom. If we're using the method that has the t-distribution, and we have an alpha of 0.05 two-tailed test, we go to the t-distribution table, and you can see my copy is all marked up. Proportion in two tails combined, 0.05, and we go down to a degrees of freedom 8, and the critical value is 2.306. And we want a plus or minus in front of it because it's a two-tailed test. So if we draw that distribution, like this. Anything that falls in this middle area, we're going to fail to reject, and anything that falls in these critical zones or critical regions, we're going to reject the null and accept the alternative. Step 3, we need to calculate the standard error for R. That is S subscript R is the square root 1 subtract R squared divided by N minus 2. So if we put in the values that we have 1 subtract 0.6 squared divided by 10 subtract 2. And that works out to 1 subtract 0.36 divided by 8. 1 subtract 0.36 is 0.64. 0.64 divided by 8, which is the square root of 0.08, which is 0.28. Let's keep 4 significant or 4 digits, 2828. Then we can plug that into our t, which is R subtract rho divided by the standard error of R. R from the question was 0.6. Rho is from our hypotheses, and that's 0. And we divide by the number that we just calculated, this one, 0.2828. And what we get is 2.121. And then in step 4, we compare the value we calculated in step 3 to the critical value that we got. And if we put this value up on this diagram, it goes about here, okay? And so that's in this fail to reject the null. And our reason or our evidence is that 2.121 is less than 2.306. No significant relationship. If we then go to B, if the sample had n equals 25 participants, step 1 doesn't change. The number of participants does not affect your hypotheses. Step 2 does, because our degrees of freedom changes, right? Our degrees of freedom is n minus 2. If n changes, then our degrees of freedom change. So we have 25 subtract 2, which is 23. And if we go to the t-distribution table, we're going to have to go down to 23. And we're going to read across, and this is somewhat difficult. I hope you have your own copy here. And the critical value that I now have is plus or minus 2.069. Okay? But this isn't the only change that happens. So we also need to recalculate the standard error for R, because that formula had n in it, right? So it was 1 subtract r squared divided by n minus 2. So now that n has changed, the standard error of r is going to change. And because the standard error of r changes, our t will change. The t that we calculate changes because we have r subtract rho. That part hasn't changed. But in the denominator, we have the standard error of r. And so since this changed, this changes. So let's calculate this through. In the numerator of the standard error of r, we still have the same piece, but in the denominator, we have 25 subtract 2. So here we're going to have 1 subtract 0.36 divided by 23. So we have 0.64 divided by 23. So this standard error of r has changed. And the revised value, where it was 0.1668, it is now, no, that's the new value. It was 0.2828, it is now 0.1668, and we're going to put this value up into this t. The r hasn't changed, rho hasn't changed, but this standard error of r has changed. So our t is now 3.597. Let's keep a few digits here. And so not only did the critical value that we needed to supersede to get into the critical region, not only did that go down, but our t actually went up. So if we draw this out, the value we calculated is now in this area. So we now reject the null, accept the alternate or alternative. Our evidence can be here, or we could write it out as 3.597 is larger than 2.069. There is a statistically significant relationship. An alternative to this process, though, of using the standard error for R and calculating the T is that instead of using, in this textbook, table B2, if instead we use table B6, we can bypass that calculation, right? So the hypotheses stay the same. Step 2, our degrees of freedom stay the same. And so I'll just do this one is A, where n equals 10. So 10 minus 2 is 8. But if we go in the Graviter and Wallno textbook, this is table B6. If you're using a different textbook or a different set of tables, it's your critical values for the Pearson correlation. And we are going to want a level of significance for a two-tailed test, an alpha of 0.05, and we're going to read down until we see a degrees of freedom of 8, and that critical value is plus or minus 0.632. And then step 3, there is nothing else for us to calculate. R has already been calculated. It's 0.6. That was in the question itself here, right? A researcher obtains a correlation of 0.6. So we bypass that. That part is already done. There's nothing more for us to do. And in step 4, we can compare, we can draw out our distribution, right? We can put negative 0.632 and positive 0.632. And then the value that was given to us in the question, 0.6, is in this fail to reject the null region. There is no relationship. There is no statistically significant relationship. And then when things change to n equals 25 participants, again, the hypotheses don't change. Our critical value does, because our degrees of freedom have changed. So we go to our statistical table here, but we go level of significance, two-tailed test, and we go down to 23 degrees of freedom, and the new critical value is plus or minus 0.396. Okay? Step 4, so that was step 2. Step 3, we bypass. It was already calculated. The correlation itself doesn't change. Put in our boundaries. And we put in the value that was calculated. And now it's in this critical zone. So we reject the null, accept the alternative. Our evidence is here. 0.6 is larger than 0.396. There's a statistically significant relationship. So there are two methods. You want to pay attention to what your professor is expecting you to do. Let me see if I can make that in focus. And it seems to me, so here, this method here uses, in the Graviter and Wallno textbooks, it uses table B6. So you have to use a different set of statistical tables, but the process is shorter.